So we've been talking about two sample tests. We're going to keep going. This is example 9. So we have a production supervisor at a major chemical company has to decide which catalyst will maximize their hourly yield. Now when I do a problem like this, I like to start off by drawing a table to organize my information. So we have catalyst XA, ZB. Okay, so he takes a sample of 5 hours for each process. So we need a sample size. It's 5 for both of them. Then for XA, the sample mean is 811, so we have sample mean. 811 and 750. And we also have sample variance. The variance is 386. And for ZB, the sample mean is 750 and the variance is 484. Assume the populations are normally distributed. Conduct a hypothesis test to see if the two catalysts have different population mean hourly yields. Use alpha equals 0.01. First thing we need to do is decide which test. Because I have a sample variance instead of a population variance, I know it will be a t-test. But for our two samples, we have two different types of tests we can use. You can use a two-sample t-test with equal variances or a two-sample t-test with unequal variances. Now in this situation, our variances are 380 and 480, but if you find the sample standard deviations, so if you take the square of the variances to find the standard deviations, you get 19.6 and 22. So 19.6 and 22 seem pretty close. And when you look at the picture of the box plots look like they have fairly equal spread, especially when you consider that your means are 811 and 750. So you're dealing with yields in the hundreds range, so having a standard deviation difference of 3 is probably not going to make a difference. So I feel safe using equal variances. Remember, you can always use unequal variances to be safe, but if your variances are equal, then you'll get just a little more power with our equal variances test. We have the alpha equals 0.01, and they told us that both populations are normal. So my assumptions are met. So next thing I actually need is my null and alternative hypotheses. The null hypothesis will be that the mean for XA equals the mean for ZB. So status quo is that they're equal. The alternative is that the mean for XA is not equal to the mean for ZB, because in the problem statement they just said, do they have different population means? It didn't say which one was greater than or less than. So it's a t-test with equal variances. So if we look back at our t-test, or our test sheet, if we have equal variances, we have this test statistic, but notice this SP squared, that's our pooled variance. We need to calculate that first using this formula. So you take each sample size minus 1 times the bias variance and then divide by n plus n minus 2. So add up the sample sizes n minus 2. So 5 minus 1 times the first variance, which is 386, plus 5 minus 1 times the second variance. So no, first variance 386, second variance 484. All over n plus n minus 2. So 5 plus 5 minus 2. And this gives me 435. Notice it's just a really fancy weighted average of our variances. Now we can plug it in and get our test statistic. X bar minus y bar over the square root of s, the pooled variance, times 1 over n plus 1 over m. So just 1 over each of the sample sizes. The biggest thing here that you need to do is, because it's x bar minus y bar, look at what order you wrote your symbols in up here. So we did xa first. So you have to do the sample mean for xa first. So we're going to do 811 minus 750. Over the square root of the pooled variance, so 435 times 1 over the first sample size plus 1 over the second sample size, which gives me 4.624. So that's my test statistic. For a t-test, we also need degrees of freedom, which are n plus m minus 2, so 8. And now we need to find our p-value. Now our p-value we put our test statistic down first, so 4.624. Now when you look at your alternative hypothesis that was a not equal to, that means that we are interested in the area in both tails. So we have 8 degrees of freedom, a test statistic of 4.6. Let's go to our t-table. We have 8 degrees of freedom. We're looking for 4.6. That puts it somewhere about here. So my area in that tail is between 0.001 and 0.0005. Now, because the area in both tails is between 0.001 and 0.005, if I add those together, or I double one of these areas, I get that my total p-value is between 0.001 times 2 is 0.002. 0.01 times 2 is 0.02. So between 0.02 and, if we times 0.005 times 2, we get 0.001. So my total p-value is between 0.02 and 0.001. If you have a calculator or applet that will do this for you, your exact p-value is 0.0017. Now compared to our level of significance, remember we had alpha equals 0.01, but our p-value is smaller than that. So we will reject the null hypothesis, which means that we're going for the alternative hypothesis, which is that they have different population means. So we found strong evidence that the population mean yields are different. We didn't say which one is higher, which one is lower, or how much they're different, just that they are different. So example 10, we want to see if a new billing system will save time. Let's draw our table again. So we need our size, our mean, and what else did it give me? Sample variance. So for an old system, we took a random sample of 45 billing times. The mean is 4, sample variance of 16. For a random sample of 60 billing times for the new system, my mean is 2, my sample variance is 5. When I look at this problem, because we have sample variances, we know it has to be a t-test. when I look at the variances, I go from 16 to 5, but based on the size of my means and the size of my samples, that actually seems like a fairly big difference in this situation because my means are only 2 and 4 days, so having a difference between 5 and 16 seems like a pretty big deal. So I'm going to go with unequal variances to be safe. They didn't tell me a significance level, let's use 0.05. And we need to check our assumptions, which is that both populations are normal or both sample sizes are at least 30 or some combination of that. And in this case, our sample sizes are 45 and 60, so both sample sizes are large. So we can do this test. Our null hypothesis would be that the mean for the old equals the mean for the new. And I just wrote old first because it was what first came first in my table. Then for the alternative, I have to figure out the sign. So has the new billing system reduced the billing time, which would mean that we'd want the new to be less than the old. So this is a greater than. Next step is the test statistic. Coming back to our formula sheet, we're going to use this test statistic, but unfortunately that also means we have to use this long formula for degrees of freedom. So our test statistic is x bar minus y bar over the square root of the first sample variance over its sample size plus the second sample variance over its sample size. So look at your chart. Because we did old first, we need to keep using old first. So we're going to do our sample means of 4 minus 2 over the square root. So first variance of 16 divided by its sample size of 45 plus the next variance of 5 divided by its sample size of 60. All of which gives me 3.019. Next, because there's a t-test, we do need degrees of freedom. Unfortunately, here we have to use the Satterthwaite approximation, which the formula looks like this. So we take each variance over its sample size and add them up and square it. And then we have to actually take each variance and square it, so we write it as sx to the power of 4, and divide by the sample size squared times the sample size minus 1. So let's plug everything in. So first variance is 16, sample size is 45. The next variance is 5 over its sample size of 60. Now remember, if they ever give you standard deviations instead of variances, you can just square them to get to the variance. Now this sx to the power of 4, because we already have the variance, we just have to square it to get to the power of 4. So 16 squared over 45 squared times 44 plus 5 squared over its sample size squared times sample size minus 1. Which gives me 64.395. Now we always round that down to the nearest whole number. So degrees of freedom is 64. Now to use my table, I'll have to round that down even further to 60 degrees of freedom. If you have a calculator, though, you won't have to round it to 60 degrees of freedom. Next, let's find our p-value. our test statistic was 3.019, and because our alternative hypothesis is a greater than, we are looking for the area in the right table. So we have 60 degrees of freedom, and we're looking for 3.019. So 60 degrees of freedom, 3.019 will put me about here, which means that I'm between 0.005 and 0.001. So when we look at this, this is a small p-value, smaller than alpha. And so we reject our null hypothesis. And basically we found evidence that mu old is greater than mu new. So that's the really short interpretation. But let's see if we can't interpret it a little bit better to something that my boss might be more interested in. So if I want to interpret it further, I might say something like, we found very strong evidence that on average, because these are means, not each individual value, but the means for the populations, the new system saves time. Okay. Notice again, my short interpretation was just that the mean for population mean for the old was greater than the population mean for the new. But my boss wanted to know if the new system saves time, so I'm going to reword it that way. So on average, the new system saves time. Again, we don't know how much time it saves, but we do know that it saves time. Okay, this is example 11. Okay. And we're going to do something different this time. So a study was conducted to see if taking calcium reduces blood pressure. 2 independent groups were chosen. One group was given calcium and one group was given a placebo. The decrease in their blood pressure was recorded. Conduct a hypothesis test to see if taking calcium reduced blood pressure by at least 1 point. Now I made a typo here when I wrote this, but what I want you to do is see if taking calcium reduced blood pressure by more than 1 point, more than taking the placebo did. So basically what I'm asking you for here is the mean for the calcium minus the mean for the placebo greater than 1. Okay, so that's what I'm asking. Is the taking the calcium reduce your blood pressure by like more than 1 point more than the placebo group did? Okay. Now this is different than everything we've done because it's not just the mean for calcium greater than the mean for the placebo. Notice it's not equal to that. Because we want to know if it's at least 1 point more. So is this difference at least 1 point? Okay, or greater than 1 point. Now, when you see something like this, we said at the very beginning when we first introduced this that technically we can look at the null hypothesis as that the difference in the means is equal to this delta. But we said that delta is almost always 0, and so we didn't have to worry about it. Well, this is one problem where we're going to work with it, where delta isn't 0, where we do have a specified difference that we're looking at. Okay, so I want to show you how to do this problem with both the equal variances and unequal variances approach, and we'll use the delta for this example. Okay, so first of all, before we pick either approach, we can still do our basics and set it up like alpha equals 0.05, and we can check our assumptions, which our assumptions is that both sample sizes are at least 30, which they're not. They're small sample sizes of 10 and 11. And also that you have to have a normal population. Okay, so if they're not large sample sizes, you need a normal population. This normal quantile plot looks fine. It's fairly close to straight line. This one's a little iffy, but, well, it's fairly close. And my box plot isn't horribly skewed. I'm going to go ahead and say normal enough. It's kind of iffy there, but we're still going to go with it for normal enough. Okay. Oh, and I forgot to mention, so the positive number represents a decrease because we were counting your reduction in your blood pressure. So this positive 5 for the calcium means your blood pressure went down 5 points. Okay, which is why we want the difference between the calcium and the placebo to be positive numbers, and numbers bigger than 1. And let's see, before we pick our approach, we can also write the null and alternative hypotheses. The null hypothesis, let's write the alternative first. We wanted to see if the mean of the calcium minus the mean of the placebo is greater than 1, which means then the null hypothesis would have to be that it is equal to 1, because our null hypothesis is always being equal. Now, some books will go ahead and write this as a less than or equal to for the null hypothesis. You can, because technically that's the alternative, the opposite of the alternative. But as far as our calculations that we do throughout the problem, our calculations are always based upon this equals. It's kind of your threshold. So for the null hypothesis, it could be that the difference is anything less than or equal to 1, but we stop at 1. So 1 is our threshold, and that's why you'll see that I just write down the equal to. So for our first part, use the equal variance approach with a pooled standard deviation, so that's standard deviation, not variance, of 7.372. Okay. The reason we're using an equal variance approach is we do know the sample standard deviations. Most of these are standard deviations. So we have to use a t-test, and I think that maybe these variances could be equal, and because specifically I told you to use equal variances. So when we write down our formula for the test statistic, our test statistic had been x bar minus y bar over the square root of the pooled variance times 1 over n plus 1 over m. But that was with no delta. If you have a delta, then all you have to do is just go minus delta. So all the formulas are the same except for you minus your specified difference. So let's go ahead and plug everything in. So notice here I have calcium minus placebo, so I need to keep in that order. So we'll do calcium mean minus placebo mean. So 5 minus a negative 0.64 minus my specified difference, which is 1, over the square root of the pooled variance. Now I only know pooled standard deviation, so I'm going to have to square it. Square that times 1 over n, which is 10, plus 1 over 11. Which gives me 1.44. Again here, I gave you the pooled variance just to save you a little time with your calculations. Okay, so we have our t-test statistic. We also need degrees of freedom. For the equal variance approach, our degrees of freedom are n plus n minus 2. So 10 plus 11 minus 2, which gives me 19. So for my p-value, if I draw my picture, here's my 1.44. Because I have a greater than alternative hypothesis, I have to shade to the right. And if I look that up on my table, it is between 0.10 and 0.05, with the exact value of 0.0832, if you use a computer or calculator. Well, that p-value, that's bigger than our alpha of 0.05, so this is a big p-value, and we will fail to reject. So that's how you do the problem with equal variances. Now let's try it with unequal variances, just so you can see the difference in the two methods, and the difference in your results of the two methods. So use the unequal variance approach with degrees of freedom of 15.591. So I calculated that part for you just to save you some time. So our test statistic would ordinarily be x bar minus y bar over the square root of sx squared over n plus sy squared over m. So basically each variance divided by its sample size. Okay, now because though we have a specified difference, we need to do minus delta. That's the only thing that changes in the formula, is we just do minus delta. Let's plug everything in. So again, it's 5 minus our negative 0.64 minus 1 over the square root. So my first variance is, well, my first standard deviation is 8.743. When you look back up at the table, notice they gave you standard deviations, so we will need to square it because we're supposed to have variances. Squared over the sample size of 10 plus the next standard deviation, 5.901, squared over its sample size, which gives me 1.41. Now we also need degrees of freedom, which they told me are 5.591, and we will round to 15. For my p-value, we're at 1.41. We're again looking for the area to the right, and it is again between 0.10 and 0.05, with the exact p-value of 0.0891. Now compare that to alpha of 0.05. That makes this a big p-value. And we will fail to reject our null hypothesis. So let's zoom out and compare our results. Okay. Notice for our two tests, our test statistics went from 1.44 to 1.41, degrees of freedom from 19 to 15, and exact p-values from 0.0832 to 0.0891. So notice we do get slightly different results for our two tests, but they are fairly similar. Okay? And what you'll see is anytime when your variances were equal enough that you could have used equal variances, you'll get fairly similar results for your two problems. If your variances had been definitely not equal, though, you would have gotten very different results between the two procedures. Okay? Also, again, when your variances are equal and it's safe to use either procedure, remember we said that your equal variances approach has just a little more power. What that means is that you're more likely to reject a false null hypothesis, which is a good thing. And the reason that you're more likely to reject it is you'll get smaller p-values. Now that we've done all that, let's just write our conclusion for our boss. Okay, so what we showed is because we rejected the null, so we went for the alternative, which is mu calcium minus mu placebo is greater than 1. So what this means that I could tell my boss is that we found, actually wait, we didn't reject it, did we? So let me just write this down so you can see it. So our null hypothesis is that mu c minus mu p was equal to 1. And the alternative was that mu c minus mu p is greater than 1. So we failed to reject the null hypothesis. Now this was what we wanted to show, but we couldn't actually quite get there because we couldn't reject our null hypothesis. But remember that we're always looking for evidence against the null hypothesis. We never look for evidence for the null hypothesis, which means that our conclusion is still always framed in terms of the alternative hypothesis. So we would say something like, we didn't find enough evidence to conclude that the mean reduction for calcium was at least 1 higher than the mean reduction for the placebo. Now, in all of these tests we've done, all we've been able to say is just whether one mean was greater than or less than or not equal to the other mean, but we couldn't say by how much or which one was, or, yeah, we couldn't say by how much. So the way that we address that is we find confidence intervals. Just like we had 3 different tests, we have 3 different confidence intervals. And again, the assumptions are either both populations are normally distributed or both sample sizes are at least 30, or some combination of the two. So if you know the population variances, then you'll use this 2-sample confidence interval. So it always starts with the difference in our means, plus or minus our critical point, and this will be population variance over sample size plus population variance over sample size. Okay. Now, if you don't know the population variances but you think they're the same, you'd use your 2-sample t-test with equal variances, which notice what changes is now we have a t critical point, and now we'll do our pooled variance times 1 over n plus 1 over m. And the degrees of freedom are n plus m minus 2. Okay. Finally, 2-sample t-tests for unequal variances. So if you don't know the population variances, but you think that they are not the same, so you think that they are unequal, then you use this formula. Okay? So x bar minus y bar plus or minus your critical point, and we'll do each sample variance divided by its sample size. But you have to use the Satterthwaite approximation of degrees of freedom. So what we're going to do is we're going to try a confidence interval for each one of the previous problems we did, so that we've already calculated our pooled variance and degrees of freedom to save us a little bit of time. Okay. So for example 12, suppose a random sample, we've already read this, so suppose a random sample of 100 waiting times observed under the current system gives a sample mean of 8.79, and random sample of 80 waiting times observed during the trial run of the new system yields a sample mean of 5.14. Assume somehow we know these standard population variances. We want to find and interpret a 95% confidence interval for the difference in the means. So, our formula is x bar minus y bar plus or minus our critical point. And I prefer to just put a z star rather than using the book's notation. So just z star for our critical point. Makes it a little bit simpler. And divide by the variance for x over its sample size plus the variance for y over its sample size. Okay. First step is find your critical point. So for a 95% confidence interval, that means I want 0.95 in the middle, which means I have to have 0.025 in each tail. Okay, and what I'm going to do is go to the z-table and look for an area of 0.025. That puts me at negative 1.96. So due to symmetry, this is negative 1.96, this is positive 1.96, and by definition, your critical point is always the positive value, 1.96. Okay. So we want to plug everything in. So x bar minus y bar. So looking back at the problem, that's 8.79 minus 5.14. Plus or minus my critical point, 1.96. Times the square root, let's see, so my first variance is 4.7 over its sample size of 100. Second variance is 1.9 divided by its sample size of 80. And now I need to put that in my calculator. And if I typed it correctly, then this is 3.122 4.17. So a short interpretation, a not as pretty interpretation, is that 95% confident that the difference in the means, now to figure out which way you wrote it, is you did 8.79 minus 5.14. So the 8.79 went to the current, so the mean for the current minus, then the 5.14, that was for the new, so the mean for the current minus mean for the new is between 3.12 and 4.17. Okay, so that's kind of a very short interpretation here, is that it's just the difference in the means is between those two numbers. But that doesn't really tell your boss much. We can make it a little bit prettier for him. Okay, a little bit simpler. So when we look at this, because we did mu for current minus mu for new, and we got positive values, which one must have been bigger? The mean for the current system must have been bigger than the mean for the new system. So we know which one is bigger. So the current system is bigger numbers, it takes longer. So we could say that we are 95% confident that for all waiting times, put in the all waiting times to represent the population and not just the sample, that for all waiting times, the average for the current system is between 3.12 and 4.17 longer than the average for the new system. So for all the waiting times for our entire population, we're 95% confident that the average for the current system is between 3.12 and 4.17 days, hours, I'm not quite sure which, longer than the average for the new system. So you can tell your boss, this is how much time we're saving. And that's how you do your confidence interval. Notice the advantage for that, other than the hypothesis test, is we can see how much of a difference we have. So for 13, a production supervisor at a major chemical company must decide which catalyst will maximize hourly yield. Okay, so we've already done all this. We know that they each have a sample size of 5, the sample mean of 811 and variance of 386, sample mean of 750, variance of 484. Assume the populations are normally distributed. Find a 95% confidence interval for the difference in the population means. Now, previously, we already looked at this problem. So because we already looked at it, we know that we are using a T confidence interval and because we already looked at it, we already decided that we had equal variances. And we decided that our pooled variance was 435 and we had degrees of freedom of 8. So our formula for our equal variances was x bar minus y bar plus or minus t star square root of the pooled variance times 1 over n plus 1 over m. Okay. Now you can decide which order to subtract these means. I'm just going to go with the order they're written in, so I'm going to go 811 minus 750. Plus or minus my critical point. So I guess I still need to find my critical point. We want a 95% confidence interval, which is 0.025 in each tail. And I have 8 degrees of freedom, so we go to our t-chart. 8 degrees of freedom, we want 0.025, so 2.306 is my critical point. So T star equals 2.306. It's the square root of 435 times 1 over the first sample size of 5 plus 1 over the second sample size of 5, which gives me 30.58 to 91.42. Okay, so this is our 95% confidence interval for, let's see, which order did we subtract them? We did 811 minus 750, so that's for the mean for XA minus the mean for ZB. So we're 95% confident that the difference in these population means is between 30 and 91. Well, what does that mean? Because we got positive values, XA must have been larger. So when we interpret it for our bus, we are 95% confident that the mean yield for XA are between or is between, so the mean yield is singular. Mean yield for all of the times you do the process. The mean yield for XA is between 30.58 and 91.42, higher than the mean yield for ZB. So we're 95% confident that the mean yield for XA is higher, and how much higher? Well, we're 95% confident that it's between 30.58 and 91.42 higher. Finally, last problem, we want to know if the new billing system will save time. So we take our sample for our old system. So for our old system, we have a sample size of 45, our sample mean of 4, and our sample variance of 16. Oh, sample variance, that's an S. We'll put an X on it because I just called these my X variables. And then for my new system, my sample size is 60. Oh, sorry there. I thought I was pausing. I was waiting for all the noisy people to go by. So my sample mean for Y is 2, and my sample variance for Y is 5. Okay. So let's find and interpret a 99% confidence lower bound. Notice we're not doing the entire confidence interval, we just want our lower bound for the difference between the mean for the old minus the mean for the new. So because I want old minus new, I need to make sure I do all the old numbers minus the new numbers. So because we already did this problem previously, we decided that we're going to use a T interval with unequal variances. And we previously calculated that our degrees of freedom are 64 once we round down. Okay. We need to find our critical point, so we want 99%, but we only want our lower bound, which means that we need 99% here, 0.01 here. 64 degrees of freedom, let's go to our t-table. See, for 64, I'll need to round down to 60, and I want 0.01 area in the tail, which puts me at 2.39. So 2.39. The positive value would be positive 2.39. My negative value is negative 2.39. However, by definition, your critical point is always the positive value. Okay, so my critical value is 2.39. So let's plug everything in. X bar minus y bar. Plus or minus, actually, we don't want a plus or minus. We only want our lower bound, so it's only a minus. Our critical point times the square root of the first variance over its sample size plus the second variance over its sample size. Let me plug our thing in. Again, the biggest thing you need to make sure you do here is that you subtract them in the correct order. So because we want to do old minus new, we need to do 4 minus 2 for my means. Minus the critical point times the square root of, let's see, my first variance is 16 over its sample size. Next variance of 5 over its sample size. Okay. And so this gives me 0.416. So 95% confident that mu old minus mu new is greater, or well, let's put it this way, is between 0.416 and infinity, positive infinity. So basically, we're 95% confident that the difference in these means is at least 0.416. Okay, or more than. Okay. So that's kind of the easy interpretation. Now, how would it be better to phrase this to our boss? We wanted to know if the new system reduced our billing times, and maybe by how much. So the old system is at least 0.416 higher. So we could say something like, we are 95% confident that for all the billing times, let's see, for all the billing times, the new system will save an average of at least 0.416 days. It might be even greater than that, but we're 95% confident that it's at least 0.416 days. And that is everything that we're going to do for our 2-sample test.